In this topic, we're going to be talking about the electromagnetic spectrum. And this PowerPoint was adapted from this author, and the material was taken from 2009. So to leave off from our last PowerPoint, we left off where light travels in a straight line. It does not bend. Now, we know that, but here's something that you need to add on to that. You need to know that light has a duality theory in the ways that it behaves. So light can either behave as a wave or a particle. A particle of light is called a photon. And here's a little comic. It says, am I an X-ray photon or a radio photon or visible? Oh hell, why worry about all that again? I'm not even sure if I'm a wave or a particle. So the photon itself is a particle of light. And we know that light travels in a straight line, but light also behaves in the form of a wave. So light doesn't really bend, the light that reflects off of surfaces that we see. However, light does travel in a wave, and that's what makes up the electromagnetic spectrum, the different wavelengths. So before we get all into this, we don't go into too much depth about photons. We focus mainly on light behaving as a wave. So let's take a look at what this wave looks like. So if we were to draw in an origin, treat this as an x-axis and a y-axis. So I'm going to draw a little line for the y, and then you guys know that this is the x-axis. Okay, so when we're looking at the light wave pattern, we always want to make sure that we are referring to things the same way. So obviously this little thing here would be the origin of the wave. This is where the wave starts at, and the direction of travel is in the right direction. Now, when we're looking at the wave, there's something called a wavelength, and the wavelength describes the length of a full wave, so a full cycle of one wave. Each wavelength, it consists of a certain distance or length, and it either goes from the peak of the wave to the peak of the wave, or the trough of the wave to the trough of the wave. So let me just draw that in there. There's the troughs at the bottom, and that also makes up a wavelength. And then there's the peak. Peak to peak also makes up a wavelength here. To describe the height of the wave, you are looking at something called the amplitude. And amplitude goes from the origin on the y-axis and down to where the depth or the height of the wave reaches. And then the displacement is the total amplitude, so just how far it travels y-axis wise. So we know that there are different forms of light. Different forms of light are produced from different types of wavelengths of electromagnetic waves. Light travels in electromagnetic waves. So these waves are produced by a movement of electrically charged particles. Light can travel in a vacuum. However, when it goes through a medium, the speed of that light ends up being a little bit different. So light travels at the speed of light, which is 3 × 10 to the 8 meters per second. So just a reference, it takes about 8 minutes for light to travel from the sun to the earth. So if you're standing on the earth and you're staring at the sun in the distance, you're actually seeing that 8 minutes ago. So the sun produced that 8 minutes ago. EM, or electromagnetic waves, are also known as EM waves, and they are transverse waves that have some electrical and some magnetic properties. When electrical and magnetic fields work together, it produces this wave-like pattern. So the electromagnetic spectrum is just a name that a group of scientists gave the groups or the types of radiation when they want to talk about them together. And the whole spectrum is the range of all of the possible frequencies of the electromagnetic radiation that we know about. So looking at this little image here, just to kind of fathom what exactly a wavelength is, if we look at the length of one wavelength, this is considered a long wavelength. The frequency of it, so the amount of times that it occurs, is much less than that of a short wavelength, which has a very high frequency. So the tendency of the short wavelengths to occur is greater than that of the long wavelengths to occur within the same time period. Let's get into what some of these electromagnetic waves look like. The first one and the longest wavelength is considered the radio wave. Now, radio waves are used in TV broadcasting, AM/FM broadcast radio, avalanche beacons, and heart rate monitors. Microwaves are the wavelengths from 1 millimeter to 1 meter in length, and they're used in the microwave ovens, which we know of, the Bluetooth headsets, and broadband wireless internet or Wi-Fi, radar, GPS systems. And then we get to the next wavelength, which is between the microwave and the visible light spectrum. This is called the infrared radiation. Whoops. And we use infrared radiation in night vision goggles, remote controls, heat-seeking missiles. Those are just a few applications. And then we get to the visible light spectrum. And this is the only type of electromagnetic wave that we're able to view with our human eyes. We know that violet is the highest frequency light, and red light is the lowest frequency light. Now, when we talk about highest and lowest frequency, we want to make sure that we're associating that with energy. So a high frequency light, it means that there's a shorter wavelength, and there's more of those wavelengths occurring within the time period than there would be a longer wavelength in the same time period. So if you've got a higher frequency, that energy is going to be higher. Lower frequency has a lower energy. Then we get to the ultraviolet light. This is one of my favorites. So ultraviolet lights are shorter wavelengths than visible light, and we use them in black lights, for instance, sterilizing medical equipment, water disinfection systems, and security images on money. There are three main types of UV light, UVA, B, and C. UVA light has the highest energy, and it cannot really penetrate through the atmosphere. It's actually stopped in the upper atmosphere. There's an extremely low risk for DNA damage because it doesn't really reach the surface of the earth, and it can destroy vitamin A in the skin. The UVB and UVC have a lower energy than UVA. However, UVB and C have the possibility of reaching our troposphere, so the part of the atmosphere that's closest to the earth. That's actually within 13,000 kilometers. And it can cause DNA damage, leading to skin cancer, and these two types of UV are responsible for sunburn. Then we get to X-rays, which are even smaller than UV radiation, and we use them in X-ray medical imaging, for instance, airport security, and inspecting industrial wells. And last but not least, the gamma radiation is the smallest wavelength, and it has the highest energy and the highest frequency of those EM waves. We use them in food irradiation, cancer treatment, treating wood flooring, and when we're using that in cancer treatment, you have to keep in mind that it's not only killing those cancer cells, it also kills the healthy cells too. That's why it's such a risk to use gamma radiation. Generally, people only use it if they're in the stage 4 and they have a lot of cancer cells that need to be treated, and they've got some healthy cells that are capable of bringing back the patient. So just a check-in question here, which of those wavelengths can you see? Only the visible light is what you can see. Why can't you see the others, though? The waves are moving either too fast or too slow for your eyes to pick them up. So our eyes are specialized for a certain wavelength, and that is the visible light spectrum here. In class, we're going to be doing an electromagnetic spectrum assignment, and when we're done this, we will jump into what a prism is. So let's go through that right now. A prism is a triangular-shaped translucent object that looks like this, and it reflects light. So when you're shining a white light through it, it actually can split the white light into all of the colors in the visible spectrum. Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. We know that visible light has shorter wavelengths and higher frequencies than infrared. And those are the types of light that we see when white light passes through a prism. And a prism is special because the shape of it allows the light to come through and show us all of the different colors that make up the white light. Red is the longest wavelength, where violet is the shortest wavelength. And then we get into something called polarized light. And when we think of the word polarized, you always kind of think of north and south poles. So let's try to bring that in to what polarized light is. When light goes through a filter, it eliminates some of those waves. When the filter, here's an example. So when the filter is like double, then we're able to eliminate many of those waves. And that is what polarized light is. In class, I'll be bringing in a pair of glasses that are polarized, and they're very cool. They end up taking out much of the light that you generally see during the day.